we are approximating the solution in a particular form. Okay, so we are going to write the assumed solution. Okay, so I had an assumed solution. As the form that would look like. So your equation is dy by dx plus p of x, sorry, dy by x square dx dy dx plus qx y equals to f of x, and we're going to assume the solution, that is, I'm going to write the solution with capital Y. That is going to have a form that looks like ak bk of x. Okay. So this is where I have constructed already the bk's of x have been defined, okay, which were basically kth bkx is centered at xk, okay, and has a bell-shaped image, okay, which is formed by stitching 1, 2, 3, 4 cubic functions and different ones, right? 4 cubic functions, okay, as shown up here, right? So these are bkx, and now by the way, I would like you to find out where is the point of inflection in this. Find out. We can do a little exercise here. Find out the point of inflection of this entire curve. Okay, this entire inflection, this spline, single spline bkx. Find out the point of inflection. You know what is the point of inflection, right? Maximum is of course here. So maximum is where the derivative is 0. Second derivative being 0 is the point of inflection. Right? So find that out. Anyways, so now okay, so what we're going to do next is, let's suppose if I decide to have this particular form of my desired solution, which I told in the last class, that is what we are doing here is we are having points going from, let's say I'm going to label them starting from 0 here and n plus 1 here, and then 1, 2, 3, 4 up to n here, intermediate ones. Okay, so minus 1, I have n plus 2. Why I'm showing these additional points to become clear? Basically, because so what you have here is, first let me just remind you that if you had certain function starting from some boundary value, let's say here it's alpha and here it's beta, okay, and it probably goes like this, I don't know, something like that, then what you are saying essentially is that you're saying that, okay, what I'm going to do next is I'm going to divide this entire thing in terms of function that is going to look like d1x will be starting from here. I will have functions like All right, so shown in the last class 12. I think I have already explained that. So here you can see that if this is your function, then these values can be adjusted by adding these different functions, okay, with certain relative weights, right? So those weights are called AKs. AKs are those weights assigned to different. So you can make this one probably bigger or this one smaller. Wherever it is bigger, for example, function goes to a higher value here. So here my BKs, if I have any BK, I can probably multiply with larger value, and other BKs will not have contributions over here. So you can adjust it so that you can actually get net value as desired by the function. Okay, so that is what I am going to. That's what this entire procedure amounts to. Okay, so we start with first thing what we do is, now one thing that we have to notice here is that um, you can actually the which BKs will actually contribute to what is the first BK, for what value of K will that BK contribute the point number 1. Point number 1 would be, I mean the value at point 1, the value of the function at point 1 will be affected by which BKs? As I told you, so if you look at this point, okay, it's affected by, if you look at, okay, so here you can see that, for example, this value at this point, there are three B's which actually contribute. One would be, of course, this one that is centered there itself. One would be centered at the next point, rightward, and there would be one centered point on the leftward, right? So this would be the other one. These three yellow colored uh, splines, okay, they all, their values, whatever their values are here, they all can have non-zero or non-zero value at the point 1. Okay, other BKs will not be, will all be 0 at the particular point 1. So basically at any K, BK plus 1, BK and BK minus 1, they will contribute, right? So that is the very important fact which makes life easier. Okay? And what makes life easier, you'll see very soon. So, but let me write it down. At any K, K minus 1, K and K plus 1 of X contribute. Okay. Other BKs are, for other values of K, if I choose beyond 1 rightward and beyond 1 leftward, then there they will not be contributing at that particular point. Okay. All right. So for example, B1 at 1, I'll be getting values from B0 and B2, right? Remember, I have value at 1. So my differential equation actually, is applicable in the entire zone, right? Starting from the first point to the last point. Okay. So I have 0th point and n plus 1th point. That is where my differential equation has to be satisfied also, in addition to the intermediate point, of course. So differential equation has to be satisfied at all points. Boundary conditions are there. So those were additional conditions we have, the boundary conditions. But differential equations have to be satisfied at all the points, right? So so now if you have the last terminal points, B0 would be contributed by BKs, which will be B minus 1, B0 and B plus 1, right? And similarly, bn, the n plus 1th point value would be contributed by bn plus 2 x, bn plus 1x, and bnx, right? So therefore, and that's it. So if you want to include the entire region and you are interested in the value of the function in entire region, in order to be fair, you have to include all the bk's starting from -1 to n plus 2. Okay, so that is why this I'm going to write down y of x ranging from k equals to -1 to n plus. Okay, this would be your assumed solution. Is that all right? Amit, it should be xk plus 1 and xk minus 1 rather than xk plus 2. I think what you wrote was probably the answer to the question that I asked, which pk's will be. If that is the answer you have written, then you should have bk of xk plus 1 and bk of bk plus 1 and bk minus 1, which are centered at xk plus 1 and xk minus 1. If you take a bk at centered at xk minus 2, that value will already be 0 at bk at the xk. Okay? bk minus 2 or bk plus 2 will already be 0 at xk. Okay, that we can see over here also in this table here also, right? The bkx is 0 for x k plus minus 1 where n is larger than 1. Okay, so if you take k plus 2, 0, k plus 3, 0, and all, of course k minus 2, 0, k minus 3, 0, so on. Only these will be where it will be non-zero. Okay. Okay, so I am going to assume this particular form, and then all we're going to do is substitute in the differential equation. That's it. Okay. Let's see what happens. So substitute. You want to substitute. So need to substitute the assumed solution in the differential equation. Okay. But before I do that, let me just again, there are certain important results which will be utilized when you substitute in, because what you're going to do is now basically I have y of x is equal to ak bk of x, k equals to -2 or -1 to n plus 2. Okay, now here how many unknown constants do I have? bk's are known to me. If I knew all the ak's, where the number of known constants to be decided, okay, that is going to be equal to k going from, so that n plus 2 plus 2, that is n plus 4, right? N plus 4 inside. Okay, so I need at least n plus 4 equations in ak's, right? If I can get n plus 4 equations in ak's, we are all set. So let's see now. So what we are going to do next is, this would be your differential equation. This would be your assumed solution, and differential equation reads, as I remember, y double prime of x plus p of x y prime plus q of x y equals to f of x. Right? This is what I have. So if I substituted there, that would give me summed over k's, ak bk double prime at x plus p of x, p of x. Let me take these constants outside. No, some other case. So p of x, I can put this over here. P of x summed over k, ak bk prime x plus q of x, ak bk of x. Okay. So this tells me that if I have this kind of assumed form of solution, then this must hold on. So this equation, okay, this equation must be satisfied everywhere. Okay. Now if it is satisfied everywhere, then what we do next is we make basically we let this be satisfied at the grid points. Okay, so therefore at xi, therefore must be satisfied at each xi. That is the discrete points, right? Where xi's are ranging from 0 to n plus 1. Okay? First point and the last point. This is the first point. Here you have to be careful when you enumerate in MATLAB the label, the A1, A2, etc. When you make the vector, element number 1 is not labeled by I equal to 0. Like in C, it's actually it starts from first index is 0, but in MATLAB first index is 1. So you have to be careful about it. Okay, but here I'm just in this discussion I'm going to assume that the first index is 0. Okay? The boundary index is 0 and the n plus 1. Okay. All right. So I equal to 0. So that would mean that at each xi, okay, I have to have a k bk of xi, bk double prime of xi, bk prime of xi, bk of xi, pxi equals to fxi. That must hold, right? So what I want to do is just let me quickly find out the forms of y's. Well, so well, actually, I shouldn't. There was no need to write. I could have directly applied. Maybe I can just write this down. Y double prime at x. Okay, this thing. Okay, at x equal to xi would be how much? So that would be ak bk double prime, right? So x equal to xi, I have summed over k ak bk double prime xi. Okay, what would be that equal to? You can see the first term. This is what I'm approximating here. So bk double prime xi. If you look at this table, okay, when bk double prime xi is, well, if xi is the same as k, then it is this value, and otherwise if it's one ahead and one before, it has these values. Okay, when xi equal to xk, when xi is the same as k, then it's this value, otherwise it is this value, and for all other cases it's 0. Okay, so that would mean that if I'm looking at xi, then all I need to look at is the I minus 1 term, the I plus 1 term, right? So that would give me a, when I choose k equal to I minus 1, I'll have a I minus 1, b I minus 1 double prime at xi, okay, plus a I, b I double prime at xi, plus a I plus 1, b I double prime at plus 1 double prime at xi. Okay. So this would mean that basically I'm looking at 3 curves, okay, and I'm looking at the point I. This is I minus 1th point, this is I plus 1th point. Okay. So the I minus 1 double prime at xi. So this function's derivative at this point, and this function second derivative at the same point, and this function second derivative at the same point. Okay. These are these quantities, right? So, and I already know those values, right? I already know those values. So these are from the other two, it is going to be 1 by x square each, and the same one would be minus 2 by x square, right? So this I can write down. That would imply a I minus 1 that minus, sorry, so that would be 1 by x square. So 1 by x square, that is that of outside a I minus 1 plus a I plus 1 by x square plus a I, that would be minus 2 by x square. Okay. So that let me just write x square. So this is minus 2 by x square, 1 by x square from the this is minus 2 by x square, then it's the same one, and All right, so that's how it is going to look like. Okay. Yeah. 1 by x square ai minus 1 minus 2ai plus 2 minus x. Okay. That is y double prime. Now, what about y prime? The bk, ak, bk prime, and that's the first term, right? Second term, I have ak, bk prime x. Again, this would x equal to xi. That's equal, sorry. So this x is evaluated at x equal to xi. Okay, so that would be basically x equal to xi. That would be equal to, again, it will be given by three bk primes. Three of these will be important. One would be I minus 1, I and I plus 1, like what we have here. So that would be A, I minus 1, B, I minus 1 prime at xi plus AI, BI prime at xi plus plus AI plus 1, BI plus 1 prime at xi. And those numbers will be that. So this, the one which is at the centered at the same I, that will be 0. One will be 1 by 2h and minus 2h. Okay? So what we get is a I minus 1 into 1 by 2h minus ai plus 1 divided by minus 1 by 2h. That's right. Plus so yeah, that will give me 1 by 2h ai minus 1 minus ai. Is that all right? So that is the second term within the summation sign. Okay. Summation sign, or as I told you, it gets reduced to for each x equal to xi. I'll have only three terms to consider in each summation, right? And that leads to much simpler form at each xi, right? So this is what you have here. Okay, let me go to the next. The last term, that is y of x. So y at, yeah, that was q of x, ak, bk x, right? Last term is ak, bk of x at x equal to xi. That is going to be equal to ak. Now again, a I minus 1, b I minus 1 at xi plus a I b I at xi plus a I plus 1 b I plus 1 at xi. Okay. So what is that going to give us is a I minus 1, b I minus, that was I think 1 by 6 or something. Yeah. 1 by 6, 2 by 3, 1 by 6. So this term will be 2/3, so the center one. So that would be AI into 2/3, okay, plus AI plus 1, that would be 1 by 6. This would be AI minus 1 into 1 by 6. Okay. That would give me basically, I take A by 1 by 6 outside, I'll have AI minus 1 plus 4AI plus AI plus 1. Okay. That is the last term. Okay, so what we did, again, don't get lost. Okay, just keep things very and keep things connected. So what we did again, I had this assumed form of the solution. Okay, I wrote it in this form. Okay, the assumed form of the solution. Okay, so this is my differential equation, and if you substitute my assumed form, it's going to have this form. Now what I'm going to do is we are going to enforce the fact that this differential equation must hold at each point in the domain, right? Whatever region I'm considering. So I'm basically applying at any point, ith point that we have constructed. Okay. So at each when you apply at each ith point, I'm going to get these equations. Okay. I'm going to get basically set of equations, right? For each I'll get a one equation. So this here I just found expressions for these. Okay, which is the first expression. First expression is this one, second is this one, and last one is the one in the next page, right? So we can just substitute it back over here, okay, and then find out how that looks like. Okay, so let me just write down. So first term was ai minus 1 minus 2ai plus ai plus 1, right? So substitute the differential equation, okay, for the point x equal to xi. Okay, I must have this satisfied, which is 1 by h squared ai minus 1 minus 2ai plus ai plus 1, okay, plus e of xi, let me call it pi essentially, which we already know. P of x is known to me, xi is known to me. I can evaluate this term into the first derivative. And first derivative had the form that was 1 by 2h ai minus 1 minus ai plus 1. Okay. Okay. That is AKBK prime, AKBK prime term. Okay, so this is AKBK prime, this is that is px at x equal to xi, this becomes pi, and this thing becomes equal to this. Okay. So that is this, and then plus q of x, that is q at xi, that becomes qi into y at xi, which is into this term, okay, that is basically multiplied with 1 by 6 ai minus 1 plus 4ai plus ai plus 1. Okay, that should be equal to f of xi. I'm going to write it in slightly different form. I'm going to take the f of xi on this side, so that is going to be nice. Okay, for each xi. Okay, and how many xi's do I have here? So for each xi, I'll have to have. So there's a question. I mean, how is b double prime I minus 1 is 1 by x squared? Well, this is what we from the table. I mean, I'm answering your question. So if you look at the table, I'm answering Amir's question first. You are asking how b double prime I minus 1 at xi is 1 by x squared. We look at this. Okay, so if I bi minus 1, okay, so bk at xk minus 1 is 1 by x squared, or bk at xk plus 1 is 1 by x squared. So what this is just for any k, right? So when you have ith point, okay, so if you have a bi minus 1, okay, this is bi minus 1, okay. So, or if you just express this result, what it means is, maybe you can write it as k. So this result tells me that bk at xk minus 1, bk double prime at xk minus 1. This is my k plus 1, k minus 1. So bk double prime at xk minus 1. So if this is my bk, okay, its derivative at this point, okay, is going to be equal to this value. And that is true for any spline. If you look at the derivative at one point before the center point, its value, this is what this result tells me. Any spline, in general, if you look at bi at I minus 1, we get this value. We'll be getting 1 by x squared. Okay. Or over here, the second derivative is again 1 by x squared. Okay. So, is that all right? So, okay. So basically, if you take that fact into account, then what you have here is bi double prime at bi double prime bi minus 1 double prime. And I'm writing this as bi minus 1 double prime at xi. What does that, what does this quantity pictorially mean? It means look at the bi double prime, bi minus 1. Okay, that means think of the uh, spline which is centered at I minus 1 at point, right? So bi minus 1 is a function that is centered at I minus 1 at point, okay? And its derivative at xi, that is over here. Second derivative at xi. So this will always be 1 by x squared. So if I choose it here or here, their value will be always 1 by x squared. That's why bi minus 1 double prime at xi is 1 by x squared. Is that all right, Amit? Did I answer your question or you have something else? Yeah. Okay. All right. So yeah, basically, remember, important thing is to remember that if I have labeled bk is centered at xk, so bi minus 1 is centered at I minus 1, and its value is being evaluated at the argument, which is xi, which is over here. Okay, it's 1 point ahead than the center or 1 point before the center. It will be the same value, which will be 1 by x squared, the second derivative value. And same logic you apply to the other derivatives as well. Okay. All right. And Satveer, you had a question. The value of b and b prime is at xi minus 1. Xi and xi plus 1. Here we have to put xi in all b. Yeah, absolutely. You have to put, basically you are evaluating at xi, right? So you are evaluating at xi, so you have to basically look at this expression. This expression I am getting at x equal to xi. Okay, that's all. So at x equal to xi, I'll have wherever x is there, I have to put xi. That's it. So is that what you're going to, what you were asking, Satveer? Was that then? Did I answer your question or not? Does bk minus 1 mean b at xk minus 1? What is b? What is b? What do you mean by b? B has no meaning. I mean, bk, remember, okay, so maybe I understand your doubt. I understand the confusion. So yeah, bk minus 1 does not mean b at xk minus 1. No. bk minus 1, I will remind you. So maybe I can remind you, bk minus 1 of x means a particular function which is centered at k minus 1 at point. That's it. bk minus 1 of x, that is what it means. In general, bkx is centered at k. If you're calling it bk minus 1, then this will be centered at k minus 1. It will have this kind of shape. It will start from k minus 3, k minus 2, peak out at k minus 1, and go back to k and k plus 1, it is 0. That is my bk minus 1x. And then I'm going to evaluate the value of these bk minus 1 at any x, and as long as that x lies between this point, and if it is these two, any of these 3 points, that will be non-zero. Okay. Okay, so if bk minus 1 value at any of the values, any of the x's which are k minus 2 or k or k minus 1 or k, that will be non-zero. Otherwise, it's going to be 0. Okay. So it depends on which x you. So now you put, all you do is you put x equal to the desired value, and then see what is the value of this particular spline at that particular x. Okay, does that answer your question? So my first answer to your query is no. Bk minus 1 does not mean b at xk minus 1. No. Bk minus 1 is a particular function which has this particular form. Okay, and that key, the labels are provided so that we know where it peaks. Where what this label essentially tells me where that function is peaking out. Okay, and then just draw the function. What 2 points this way, 2 points that way, rest of the points here. That's it. So Satvi, is that all right now? Or still I have doubt? Satvi, did I answer your question? No, no, don't look later. You just tell me now. Why do you want to look at it later? So you just get it done now. Why do you want to delay this? Why do you have to delay? Because now if you already have serially, okay, anyway, just look at it and let me know. All right, and proceed. Okay, but just remember that b of any index essentially means that that's a particular function. That's a one particular kind of spline function which peaks at that particular xi, which is the labeled vix is peaking at xi. Vi minus 1 will peak at xi minus 1 and so on. So take a look and then let me know. Okay, so this is your equation and this would hold at each point, since hold at each point. So how many points do I have now? Can anyone tell me how many such equations will be obtained? Okay, can anyone tell me how many such equations will be obtained? Okay, so I have an answer n plus 4, one answer is 1, n plus 4, one is n, 1 plus 1, n plus 2, all kinds of answers. So as I told you, no, we are not used, no. Okay, Rohit, here I have not used, remember what I told you. The differential equation applies to all the points, no matter whether it's boundary or intermediate points. Okay? So this is basically a differential equation. I'm applying the differential equation because I'm substituting the differential equation. Okay? So this is essentially this equation is nothing but the form of differential equation, the form the differential equation takes after substituting your assumed form of the solution. Right? This is applying differential equation. Differential equations are applied at n plus 2 points. Okay, so correct answer as Virgia gave it is n plus 2. Okay, so yeah, so this is n plus 2 equations will be obtained. Okay, that means I going from 0 to n plus 1. Okay, all the points, all the points, okay, including the boundary points. Okay, and remember how many unknowns did I have? N plus 4. Okay, so I had n plus 4. I have gotten already n plus 2 equations. Okay, how do I get the other equation? Other two, for the boundary conditions separately. Okay, so the other two equations are given by the boundary condition. Remember, boundary conditions are completely independent of the differential equation, right? So those boundary conditions, if I apply y at x0, that is equal to alpha, and if I just use the back again, y at xi is given by a particular form, that is turned out to 1 by 6 a minus 1 plus 4 to 0 plus 3 and y at x n plus 1, that is equal to beta. That is implied, right, is a minus 1 of 0 plus 1 and then here I get an plus 4an plus 1 plus an plus 2 equal to. These are the two additional equations I will get. Okay. In addition to these equations. Okay, so let me write this. Let me write this equation particularly in order of increasing xi. So what I'm going to do is I'm going to ai. So remember these are my unknowns. Okay, I ranging from 1, 0. Sorry. So all the ranging from I equal to 0 to n plus 1. That would be my unknowns, right? So I have values going from a minus 2, a minus 1, a0, and so on. So we collect the terms and write down. So for example, I minus 1 together, I together, over here and here, and I plus 1 over here and here. Okay. So if I just write that down, and well, maybe I can, first thing I can do is multiply with h square over here, so that this gets cancelled out. Okay. So this gets cancelled out, maybe 2h square. So 2h square, so that I have 2 here, and then 2h square, I get h here, and then 2h square here, and then 2h square here. Okay. So I just multiply with 2h square everywhere. Okay. So this would be actually 1/3. So this would be x square by 3. Okay. So let's see. Coefficient of ai minus 1 is how much? So coefficient of ai minus 1 is, let's see, ai minus 1, that is 2 plus hpi plus h square qi by 3. Okay. So we can write that down as 2 plus hpi plus h square by 3 qi. Okay. Everything is known, pi is known, h is known, qi is known. Okay. This is a constant for ai minus 1. Similarly, coefficient of ai will be equal to minus 4 here, and there's no ai here, then 4 qh square by 3. Okay. So that would be equal to minus 4 plus 4 a 4 qi h square by 3. qi h square, okay. And coefficient of ai plus 1, that would be equal to, we have 2 here, same as ai minus 1, except that this coefficient is still the same. This will become minus, and this still remains the same, right? So just one of the term, the ai minus 1 term becomes negative. So this minus plus hpi, it becomes minus hpi. Other two terms remain the same. So this will be 2 minus hpi plus h square qi. That's it. Okay. And then I have, so these will be the terms, and then there is additional constant term, which is not dependent on ai, right? But it's a constant. Okay. So I can write that down as so next page, that would be equations in ai. Okay. So what is that? First one is ai minus 1 multiplied with 2 plus h square plus h square 3 qi. t plus ai plus square pi t, okay, and then ai plus 1 is exactly the same except that one of the terms is negative. 2 minus fpi plus f square qi by 3, okay, and then there's one term with xpi ai, and we having minus 4 plus 4 qi square by 3. Please check that algebra. Minus 4 plus 4 qi square, which by 4 qi x square. All right, so that plus um, minus 2x square fi, right? So minus 2x square fi. I don't have 2x square. Okay, so this is your for I equals to, for all I ranging from 0 to n equals to. Okay, that will give me, so that would mean that I'll start, for example, when I equal to 0, I'll have, I can, so for I equal to 0, I know x, so when I equal to 0, I know x is 0, okay, and I can calculate e at x0, q at x0. So again, given xi, I can evaluate first p, q, so start with I, okay, equal to 0, okay, and each I find out pxi and qxi, right? This way, you will have an array stored for pi and qi, right? So you already construct pi and qi essentially. Begin with, start, construct pi and qi and fi, of course, is also, and f of xi, which is fi. So these numbers you already calculate, you basically construct in the beginning itself, and then you will have these numbers known, and then you construct this linear system. Now it's nothing but a linear system, right? So what you have here is a minus 1 plus something plus, so I equal to 0 case would look like ai minus 1, a0 into something plus a1 into something, and then all zeros giving me 2x squared f0. Okay, I equal to 1 will start from a0 into something plus a1 into something plus a2 into something with square of 1, and so on. This will be 0. Okay. So this way, actually, you can see that you will form a tri-diagonal kind of, and then there is additional 2 more equations which we just listed down earlier, which were these ones, right? a0 and a1, and a minus 1, a0 and a1, an plus 1, and plus 2, right? What you can do actually is, from these, one way to do this would be, actually I can calculate a minus 1 in terms of this quantity, that is 6 alpha minus 4a0 minus a1, and here I can calculate an plus 2 as 6 beta minus 4an plus 1 minus an. Okay. This I can do, and these I can substitute in the first equation where I have a minus 1 appearing, and the last equation when I equals to n plus 1. Okay, I will be having terms like a n plus 1 minus 1 is n, a n into something plus a n plus 1 into something plus a n plus 2 into something, okay, and then all the terms are 0. That would be equal to 2x squared fn plus 1. Okay, what I can do is I can substitute a minus 1, okay, and a n plus 2 in these two equations in terms of a0, a1, etc. Okay, so that is what we got here, right? So a minus 1 is substituted, a minus 1 will be having this form, okay, and a n plus 2 will be having this particular form, right? So this is in terms of a n n plus 1. This is a0, a1. There is no a minus 1 and a. So that way we will get rid of the terms a minus 1 and a n plus 2, okay, and everything will be expressed in terms of a0 into something plus a1 into something, and on the right hand side you will be having a constant um, set of constants, right? So this would be essentially, so after substituting the boundary conditions, so we use boundary conditions to substitute for a0 and an plus a minus 1 an plus 2 in the first and last equations above, so that final form is as follows. Final form will be some constant into a1, that would be having a11 into a1 plus a12 into a2 plus a13 into a3, and then this will become 0 equal to some constant b1, then a21 a1 plus a22 a2 plus a23 a3, okay, plus so on, okay. You will basically get the third one would, so if you look at this, first one start, sorry, a0, it should have started with 0, okay. 0, 0, 0, s1, s2, etc. s0, s1, s2, okay, and so on. Okay, so if you look at this, that is what you are. So you will get rid of this term. This will be expressed in terms of a0, a1. Okay, so the first term will be a0 into something plus a1 into something, and take the constant terms on the right hand side. Okay, only have, so this constant will be changed because this one, if you substitute for a minus 1, okay, there's a constant that is 6 beta appearing here. And similarly, if you look at a sorry, a n plus 2 has 6 beta, a minus 1 has 6 alpha. Okay, other than for a0 minus a1, I have 6 alpha appearing here. So when I substitute it back over here, a minus 1, let's say, then that's a constant, and there's another constant 6 alpha. There'll be a constant term, so that I can take on the right hand side. That will be actually 2x square f0 minus something will appear here, and then everything else is a0 into something plus a1 into something plus a, etc. Okay, and this will be having essentially the form that would be a tridiagonal matrix. Okay, so that would look like this kind of form, right? So it will have this kind of form, and so this can be written as a into a equals to b. Okay, this form. Okay, so I'm going to leave it to you to find out how each term of a matrix look like. Okay, so what is the a matrix element? Okay, to find out a matrix element and b vector element. Okay? This is a linear system. Okay, so I'm going to do a little bit of exercise here. So exercise is just do this calculation. Okay, do this substitution and eventually find out. So find out the form of or elements of A and B. Okay. And then you are all set. All you need to do is, if I have constructed A and B, all you need to do is just solve this linear system. That will give solve, get AI, where I is ranging from 0 to 2. Okay, so once I have solved for AIs, okay, I'm done, because now you give me X, I can give you the predicted value. Now you can plot your function by just going back to your desired assumed solution. Okay, your assumed solution is AK bkx. So I know AK is going from -1 to n plus 2. Okay, and you know all these AKs, and you know basically BKs are known to me anyway. Okay, so you give me X, I can find out Y of X. Okay, and that way for each Xi's you can do that and plot it out. Okay, so that would be your procedure for implementing this particular method. Okay, let me remind you, there is a homework due. It's Tuesday or Wednesday, maybe. Or I think it was Tuesday. Please submit your MATLAB codes by Tuesday. Okay, it was about the actual dispersion EFR with actual dispersion, applying shooting method. Okay, and in addition, of course, do this, which I just told you to find out the form of A's and A and B. Okay, and that's it. You may give it a thought on how to apply Neumann bound. If I have a Neumann boundary condition, what would happen? That means if here, remember, the boundary condition that we used was y at x0 and y at xn plus 1. These are Dirichlet kind of, right? And the values satisfy values given at the end. If instead we had a derivatives or one of the derivatives given or the derivatives given at one of the endpoints or the both the points, how would you have proceeded? How would you have proceeded? What changes would have been needed to be made so that you can solve this? Okay. So I guess next class I'll try to do some questions, okay, and some MATLAB examples, okay, because this is basically we have finished kind of the methods related with OD. Okay, I want to step back and just apply these methods to various different kind of problems. Let's see how many of them we can try. But in the meanwhile, this will be only productive if you have given it a thought as well yourself, right? Please at least do the homework that I gave you so that you are all set for discussion. Okay, so and following this, we'll start the PDF. Okay? And let's see how far we can go. I had a lot of things in mind, but maybe I was thinking of doing some machine learning part in this course. Last time I was not able to do it, but let me see. I'm not sure. Anyways, fine. So I will stop the class today. And any questions? That would be helpful. What would be helpful? Amit, what did you mean by that would be helpful? You mean machine learning? Yeah. Yeah. I want to definitely. I want to do that. See, it's a thing is that had it been a course that I was doing earlier, only chemical engineers were there, and then I could have managed. But now that petroleum engineers are there, so I have to also cover some reservoir. Essentially, these are PDs only, but applied to reservoir. So that takes some time. I have to look. I don't know. I have plans, but depends. And also, I have missed 3 classes, so I have to cover them. So what I'm going to do is every Saturday, next 3 Saturdays, we'll assume that this class is scheduled. Okay, I'll send out the invitation. Please join. Okay, please let the others know as well. Saturday 11 o'clock. Next 3 Saturdays I'll take additional classes. Okay, all right. Okay. Any other question? I'll try to do the machine learning part, but let's see how much. Maybe some of the things I may have to compromise and not. Let's see. Okay, I'll stop then. We'll meet on Monday or Tuesday. Bye bye.